Right, now we look at Newton's second law. Now, you have to always compare Newton's 1 and Newton 2 and make sure you know what you're working with. The moment that you have acceleration, then that will tell you there's an F net, right? And immediately you will start that by writing down F net equals M times A. But if you are at rest, or at a constant velocity, then you must know that you are working with Newton's first law, and the way to start is to say F net is equal to 0. Now let's look at two applications of that. Now the first one, they tell you a cat glides down at the inclined plane at a constant, and there they give it to me, constant velocity, right? The mass of the cat is 2 kilograms, and they tell us to calculate the kinetic coefficient friction. Okay, so we know looking for mu k. Right, what do I know? Constant velocity. The moment that you have constant velocity, I will start by saying, since the velocity is constant, I know I'm working with Newton's first law, right? Newton's first law, right? And that tells me F net is equal to 0, or if you prefer, you can write down M times A and then substitute that A with 0. So F net is 0 is my starting point because I'm working with Newton's first law. Right, now to know what is F net, let's go and look at all the forces working on that cat. Now obviously it's got a gravity, but let's immediately resolve that gravity into a perpendicular and a parallel component. Then we know there's friction, right? Now friction, if it glides down, friction is definitely working in the upward direction, and you've got a normal force, right? Now for Newton's law about motion, I'm not going to look at that direction perpendicular to the movement, because in that direction it's not moving, right? So I'm going to start out by looking at the direction of movement, and this cat is moving down, so that will I take as the positive direction. So here I will say the net force is adding all the forces together, so I must add forces. And what am I adding? I'm adding gravity parallel, and that is in the positive direction, and to that I'm adding the frictional force, but that is in the negative direction, right? Now gravity parallel, that's the whole gravity, which will be 2 times 9,8. And for the parallel one, I need to times sine of 35 degrees there. Minus, now for the frictional force, that will be mu k times the normal force. Right, this ends up being 11,242 or whatever, minus mu k. And now I have to think about the normal force. Now, when I think about the normal force, I'm going to look at this perpendicular one, because it's not moving in this direction. I know on an inclined plane that normal force is just equal to gravity perpendicular. So that will just be gravity perpendicular equal to 11,242 minus mu k. Right, how do I get gravity perpendicular? That will be the whole gravity times cos of 35 degrees. And that always together is 0. So I solve for mu k, and when you do that, you end up with 0,70. Just don't drop that last 0, right? There must be 2 places after the comma. Right, so here the fact that it was constant velocity was telling me I'm working with Newton's first law, telling me I have to start with F net equals 0. Right. Right, in the next question, the crate has a mass of 5 kilograms and the crate accelerates at 0,2 meters per second squared to the right. Now, immediately accelerate. That's going to tell me I am working with Newton's second law, right? Newton's second law. And then we always start with F net equals M times A, right? Because it's accelerating, there will be a net force to the right. And once again, they ask us to calculate the coefficient of friction, right? So we're looking for mu k again. Now, let's start by drawing a free body diagram. Even if they don't ask you for a free body diagram, I need a free body diagram to think. So here I'll take that 6 and I will replace that with an Fy and an Fx, right? And then obviously there's also gravity. If it's moving to the right, then to the left you will have the the kinetic friction, and there's also a normal force in the upwards direction. Now, if I'm working with Newton's movement law, I'm not looking at the forces perpendicular to movement, I'm looking at the forces in the direction of movement. So that is going to be my positive direction. Right, so here for F net, that will be Fx plus minus Fk to be equal to m times a. Right, how do I get the x component? That will be 6 times cos 30. Right, I have the angle with the horizontal. Right, minus, I'm looking at the frictional force. That will be mu k times n, and that will be equal to the mass of 5 times the acceleration given to me, 0,2. Right, so here I end up with 5,20 and minus mu k, and now I have to think about the normal force. Now, what do I know? I've got an upwards y component, so it's helping my normal force. My normal force will be smaller. So here the normal force is gravity minus Fy, which is equal to 1 there. Right, so 5,20 minus mu k, we get the whole gravity, and that will be 5 times 9,8 minus, and then the y component will be 6 sine of 30. And all of that is equal to 1. Right, so then you just have to solve for mu k, and you end up with a 0,09. Well, that is very small, so this must be a very smooth surface. Right. Okay, so this is for one object, but what they want us to do is they want to do systems with two objects. Now here you've got two that is connected with a piece of rope. And with a rope, you have to remember a rope pulled on both sides with the same tension, right? It can't pull more or less on any side. It pulls with exactly the same tension there and there. Right, now the question over here is the coefficient of friction between A and the surface is given. So mu k there, 0,2. The pulley is frictionless, and now they ask me that tension in the rope. Right, so first off, let's take components of everything that's not in the direction of movement. Now over here we don't have a problem. The gravity and the tension in the rope are both in the direction of movement, so there's no components. This one, the force that's going to be a problem is going to be gravity. So we are going to take gravity and resolve that into a parallel component and a perpendicular component. So here for the parallel component, that will be 2 times 9,8, and for parallel, that will be sine of 25 degrees. And if you do that, you end up with 8,28 newtons. Right, and that will be down the plane. Right, moving on. Getting the perpendicular one would be 2 times 9,8 times cos of 25. And for that, you end up with 17,76 newtons. Right, so first I've converted that gravity and replaced the gravity with the two components. Right, okay, next up, free body diagram. Now this one is actually the easier one. It's hanging still, so there we only have the tension in the rope and the gravity. It's not on a surface, so we won't have a normal force, we won't have a friction force. Right, now we're looking at this one. Now immediately I've got the rope with the tension up there. I will have gravity parallel pulling it down. I'll have gravity perpendicular working in that direction, and I've got the normal force working in that direction. And now I need to add the frictional force. Now before that, I need to know in which direction is this thing moving. Is it moving in that direction or is it moving in this direction? So let's just look at it. We can ignore friction at this stage because friction can't make something move. It's always opposing friction, opposing movement. So here what's pulling it down is actually the gravitational force on this one, and that will be 10 times 9,8. So you have 98 newtons pulling this whole system in this direction. Right, what's pulling it in that direction? Well, in that direction is actually pulled by the parallel component of that gravity, and that will be 8,28 newtons. So who's pulling harder? This side is pulling harder. This whole system is definitely moving in that direction, right? So if this one is moving up the plane, if that is the direction of movement and therefore the positive direction, then that tells me friction is going to be in the downward direction, right? So this one is going to move down, that one is going to move up the plane. Now, normal force. Now Q is obviously not on a surface, so no normal force, no friction. We're working with this one. What do we know? Now if you look at the perpendicular ones, right, then you will see that the normal force is just equal to gravity perpendicular. We've already worked that out as 17,76 newtons, right? Then to get the frictional force, right, mu k is given up there as 0,2, so that's just multiplying by 7.6, and then you end up with 3,55 Newton over there. Right, then we get to Newton's second law. Now, F net is equal to m times a. F net is equal to m times a. Right, the CAPS is very specific. You may not apply Newton's second law to the whole system, right? You need to apply that to every object apart and then do simultaneous equations. Right, so let's look at this one. Right, it's moving up the plane. Now, F net is the sum of all the forces, and we're looking at all the forces in the direction of movement. Now, T is a positive force, so that will be T plus minus Fg parallel plus minus Fk. That will be equal to m times a. So you have there T minus that parallel one, we've already worked out 8,28, minus the friction, we've already worked out 3,55, and the mass of this one is 2, and a is also unknown. So I've got two unknowns, but I've got a second object to work with. So let's just write T equals, and that will be 11,83 plus 2a. Right, moving to the other side. Now the positive direction is the downward direction. So adding the forces together, Fg is a positive force and T is a negative force. And then you'll end up with 10 times 9,8 minus T being equal to 10a. And T ends up being 98 minus 10a. Right, so now I've got two expressions for T. And what is that T? It's not the whole force T, right? It's not the whole tension force, because they are not the same, right? But I've already had the minus and the plus added there. So the T in my equation is just the magnitude of the tension. And obviously the magnitude is the same. A rope pulls on both sides with the same tension. So yes, these T's are the same. So 11,83 plus 2a is equal to 98 minus 10a. I end up with 10a being 98 minus that 11,83 and ending up with an a of 7,18, and that is meters per second square. And if they asked me for the acceleration of p, for p it would have been up the plane, and for Q that would have been down. Right, but this time they only ask us for the tension. And now you have a choice of working with this one or working with that one and substituting A back into that. So if you work with this one, it ends up being 11,83 plus 2 times A, which was 7,18, and that gave you 26,19 newtons. Or if you use that one, and that was, you only had to do one, was 98 minus 10 times 7,18, ending up with 26,20, just a little rounding difference. Right, so let's move on and do one more. Now in this one, the kinetic coefficient of friction between block A and the surface is 0,2. So mu k 0,2 over there. The pulley is frictionless, and the question is calculate the tension in the rope. And once again, the rope pulls on both sides with the same magnitude force, right? So even though the forces are not the same, the magnitude of those forces are the same. Right, so for B, B is in the direction that it would be moving, so there will be no components. For A, it is the applied force that is in a weird direction and not telling us enough. So we are going to take that applied force and make that into an X and a Y component. So for the X component, that will just be 20 cos 30, and you end up with 17,32 Newton. And for the Y component, that will just be 20 sine 30, ending up with 10,00 Newton. Right. Now, guys, take a moment, pause the video, and complete this question, and then come back to see if you are where you are supposed to be. Right, I hope you've done that. Let's just check if you are correct. Now we have to draw free body diagrams. Now for this one, it's easy. There will be gravity downwards and there will be tension in the rope upwards. For this one, there will definitely be gravity down. There will be a normal force up. You see the rope, so you know there's tension there. And what are we going to do with that one? I am going to resolve that in an Fy and an Fx. But we're still not finished. We still need the frictional force. And for that, I need to know where this thing is moving towards. So here we've got gravity pulling, the gravity of this one, which is 98 newtons, pulling it down on this side. And on that side, the only thing pulling is that X component. And we've already worked out that is 17,32 Newton. So obviously the pulling on this side is bigger than the pulling on that side, and this whole thing is moving in this direction. And that tells me the friction on this one will be to the left. Right, now guys, I can't stress enough that you have to take your time on the free body diagrams. If your diagram is wrong, then obviously you can't have the equations right. Okay, let's start with normal force. Now, that one is not on a surface, so there's no normal force, there's no friction, but this one is on a surface. So let's think about the normal force. Now, for normal force, we're going to think about this perpendicular direction. That one is not moving up and down. So in this direction, we have to get a 0, right, as our net force. And you see that the Y component is helping the normal force to keep this object from sinking in. So the normal force will be smaller than gravity by the Y component that's helping it. Right. Next up, gravity. Now, we're working with the 5 kilogram one, so that will be 5 times 9,8 minus the Y component of 10 that we've already calculated up there. We'll end up in 3900 Newton. Right, then working out the friction. That is just mu k times the normal force. Mu already given to us up there. Normal force we've just calculated, that was 39. And then you end up with 7,80 Newton. Okay, so now we're ready to do Newton's second law. And we're going to apply to every object separately. So here we're going to say F net equals m times a, and there F net equals m times a. Right. Now, remember, now we are going to look at the direction of movement, and it is moving to the right. So here, this will be t plus minus fx plus minus fk, that is equal to m times a. T is the unknown. That fx, we've already calculated, it's 17,32 minus, and then the frictional force we've also worked out 7,80, and the mass of that one was 5, and a is another unknown. So here we end up with our 25,12 plus 5a. Right, so check your maths if you had this correct. Right, to the right. Now this one is moving down, so here it is going to be fg plus minus t, that is equal to m times a. Now gravity here, 10 times 9,8 minus t equal to 10a, and you end up with t being 98 minus 10a. Right. So now you have the two equations, and remember, even though the forces are not the same, the one is in that direction, the one is in that direction, the magnitude of the forces are the same, and this t is only standing for magnitude. We already had the plus and the minus for the direction. This is only magnitude, and therefore 25,12 plus 5a will be equal to 98 minus 10a. I'm solving for a and ending up with 4,86 meters per second square. And obviously for a, that will be to the right, and for b, that will be down. So a to the right and b, that will be down. Right, but we still haven't answered our question. The question up there was calculate the tension in the rope. So for tension in the rope, we're just going to substitute back. So here we end up with T being 25,12 plus 5 times 4,86. If you do that, you end up with 49,42 newtons. Or you could have chosen the other one, right? So there it would have been 98 minus 10 times 4,86. to give you 49,40 round. Little rounding difference. Right, guys, you have to go and practice this now and look at all the old exam questions that's got similar questions. Next up, we're going to look at Newton's third law.